Welcome back to part 2 of this series where we learn how to determine the order and rate constant of a reaction. We ended off with question number 2, which reads, consider the following reaction, and the initial rate of the reaction is measured at several different concentrations of the reactants with the following results, just like in question number 1. Notice the table here, and we have the molarity of the reactants shown in these two columns and their initial rates. And from this data, determine the rate law for the reaction, and for B, the rate constant K for the reaction. So we'll have two rate laws, one for this reactant and one for this reactant. Let's start with CHCl3, known as chloroform. We'll be using the exact same formula as before, where we have rate 1 over rate 2 is equal to a constant K times the concentration of the reactant, and we'll call that first reactant A raised to the power of n, subscript 1, over the constant K times the concentration again of A, but of course at a different reading, raised to the power of n, subscript 2. When it comes to picking the two rates, you want to pick when the concentration is actually changing. So take a look. It changes from here to here. It doesn't change from here to here, so skip that one. Or you can choose a change from here to here. However, the first two rows are best since the concentration of Cl2 doesn't change during that time. So this is rate 2 and that's rate 1. I'll replace rate 2 with 0.0069 and rate 1 with 0.0035. Just like that. And that's equal to the constant K, which we don't know, times the concentration at rate 1, 0.010. And this is in molarity, so we have moles per liter. Don't forget that. Raised to the power of n. And you don't need to write down the subscripts. We can keep track. The rate constant again, and the concentration of 0.020 moles per liter raised to the power of n. All we have to do is solve for n, and that will give us the order of this reaction. The k's will cancel out, and to solve for n, we'll need to use logarithms. So I'll find the answer to this, known as the quotient. Anytime you have a fraction and you reduce it down to a number, it's referred to as a quotient. So that divided by 0.0069, and we get 35 over 69. Of course, some calculators don't give out the fractions. You might see instead 0.507. It's okay. Whatever you find, you can place it in there. And that's equal to these two, 0.010 over 0.020 raised to the power of n. This expression and this expression mean the same thing. Okay, now to solve for n, we log both sides or ln both sides. It's up to you. So you can either log or ln. I'll stick with log. And by logging both sides, this exponent actually becomes a product of that expression. So we have log 35 over 69 is equal to n times log of this fraction. Dividing now both sides by log of this fraction, and we end up with n. So log of 35 over 69 divided by log of 0.010 over 0.020. And we end up with an n value of 0.979 rounded up. That's equal to 1. So this is a first order reaction. We have to do the exact same thing for Cl2. Let's analyze the numbers here. We go from 0.010 to 0.010. There's no change, so don't select those two rates. However, there's a change in molarity from here to here. And there's also no change in the chloroform concentration, so it's a good selection. So we'll use these two as our rates. I'll call this rate 2 and that one rate 1. Let's do our work on the side using the exact same formula as before. I'll do this quickly now since we know what to do. 0.0069 over 0.0098. That represents rate 1 and rate 2 equal to K, and the concentration, in case you can't see, is 0.010 molar again, and 0.020, both being raised to the power of n. If you solve for n the exact same way we did in the previous calculation, you should end up with an n value equal to approximately 0.50. And what this tells us is that this is a half-order reaction. Let's move on to question B. They actually want the rate constant K for the reaction. So in the previous calculations, K was cancelled out, but now we can actually find K. And the way you do that is we take one rate, let's take this one as an example, 0.0035, and we'll use the formula K times the concentration of the first reactant. So we have 0.010, 0.010, and that's being raised to the power of 1, which is what we found in part A. In addition, we'll be multiplying that to the concentration of Cl2, 0.010, and that's being raised to 0.5. Now this part is tricky. This has a unit of molars, and this also has molars. So we have K times 0.010 molars, and over here we have 0.010 raised to the power of 0.5 molars 0.5. Now remember, anything raised to the power of 1 is itself, so that's why I didn't put a 1 there, but by all means you can do that. Let's use our calculator to multiply out the numbers only, so 0.010 times 0.010 raised to the power of 0.5. This gives us 1 times 10 to the power of negative 3. So K, 1 times 10 to the power of negative 3. And the molars, we have molar times half molar. Using our algebraic laws of exponents, this is molar 1.5. Essentially, we're adding 1 and 0.5 together. We need this to figure out the units at the very end. Now, to solve for K, we divide both sides by this number that we found. And remember, this number is being carried all the way through. That has units of molars per second. So dividing 0.0035 by the answer that we found previously, we get 3.5. 3.5 is equal to K. To figure out the units of 3.5, look at this. We're dividing molars per second divided by molars raised to the power of 1.5. When it comes to dividing out numbers, you reciprocate and change the sign. So we have molars per second, we reciprocate that, and we end up with 1 over molars raised to the power of 1.5. Again, using the laws of exponents, 1 minus 1.5 is molars raised to the power of negative 0.5. And rather than writing per s, we can write down molars negative 0.5 times seconds negative 1. And so this will be the units of our constant. And there you have it. That is how to determine the order and rate constant of a reaction.